Anyway, it's wonderful to see you all here. As Jim said, I'm a past president of the ASP and vice president and board member. I think I served for a total of 8 or 10 years, actually, if you count past president. And ASP is very dear to my heart, and it's great that they are putting on this meeting to ensure STEM literacy, and I've had a lot of sessions among professionals in that regard. And by the way, I know that there are quite a few professional astronomers here, but my talk will be aimed more for the general public component. So forgive me if I define a few things that you already know, okay? But anyway, STEM literacy is really very, very important, and ASP's efforts in this regard are to be much applauded. Of course, we can't do this for free, and we've had this wonderful public lecture series, 4 amazing speakers on Sunday, and then you need to settle with me tonight on Monday. It was all free, but that doesn't mean that we won't welcome donations, okay? So in fact, there will be a hat at the back of the room there. I think Cindy has it, right? And if you wish to give a donation of any size, we would much appreciate anything and everything that you're willing to give. Everything counts. All right, well, let me talk a little bit about comets. Comets appear as sort of diffuse, luminous patches in the sky, often with long tails. Here's Comet West, 1976. And they move slowly among the stars from night to night. They're visible typically over a few weeks, maybe a month or two, in the best cases, sometimes only a few days. But they don't go streaking across the sky like a meteor or a shooting star. I'll have more to say about that later. Here's one of my favorite ones from a few years ago. Actually, it's been quite a few years now, 16 years. Comet Hale-Bopp. It was magnificent. How many of you saw Comet Hale-Bopp? Oh my goodness. I shouldn't have to define what a comet is. How many of you didn't see Hale-Bopp? There's not many 7-year-olds here. Well, I should say 16-year-olds or even 20-year-olds who have a hard time remembering. I remember it, I guess, because they were only 4 years old. That was a very nice one. And then more recently, in January of 2007, there was Comet McNaught, which was wonderful in the southern hemisphere with this incredible curving tail. Again, a meteor is not a comet. I was at a star viewing session with another group just a few nights ago, and a meteor right went streaked across the sky, and someone said, "Whoa, we just saw a comet." And I had to politely correct them that this was a meteor, not a comet. And they said, "Oh yeah, we heard about those things. Falling stars, shooting stars, right? So there's not a star up there anymore." And I had to explain that no, it is not a falling star. It's a little grain of sand, at best a little pebble, zipping through the atmosphere at such a high speed that it burns up. Okay, but it's amazing among the general public how much confusion there is, and this is part of the reason we need to do more STEM-type education. Here was a wonderful one, Comet Mikeyaseki, by many accounts the best one of the 20th century. But of course it depends on whether you focus on length of tail, or total brightness of the nucleus, or total brightness of the tail, or whatever. In any case, there it is. And indeed, the word comet comes from the Greek long-haired star, Aster Cometes. And I see the edge of the screen killed my end quote mark. I do know that it's supposed to either. But anyway, so Aster Cometes, right? So the Greeks sort of thought that these looked like stars with long hairs, and so that's where the name comes from. In ancient cultures, comets have been widely viewed as bad omens, messengers of the gods, basically proclaiming that there's going to be some sort of terrible disaster coming, essentially harbingers of doom, warnings of death and destruction from the gods. And indeed, you can see in William Shakespeare's Julius Caesar, "When beggars die, there are no comets seen. The heavens themselves blaze forth the death of princes." And it could be that among even some people in the world today, they are thought to be this way, just like solar eclipses or thought to be bad omens. And indeed, you know, there have been some Chinese astrologers who didn't correctly predict an eclipse. This was thousands of years ago, and they were apparently beheaded for it because, you know, you have an eclipse and no one predicted it. It looks like it's bad news for the emperor. Emperor says off with his or her head. Anyway, same thing with comets. You know, they've been viewed as very harmful things. In general, of course, they aren't harmful. Sometimes they are. That's not going to be the point of my talk tonight. But occasionally they do crash into the Earth, and so we would like to have an early warning system. The dinosaurs didn't, and either an asteroid or a comet caused their demise, along with 2/3 of all other living species during the Cretaceous-Tertiary extinction 65 million years ago. Okay, well, what is the true physical nature of a comet? A comet is basically a dirty ice ball or an icy dirt ball, depending on the relative mixture of ices and dust and rocky material. And it comes in from the deep freeze of the outer solar system, either the Kuiper belt or the Oort cloud. I'll define those a little bit later. And as this dirty ice ball gets closer to the sun, the ices start sublimating. They go directly from solid to gas. And the proper term for that is sublimating, although we often just say evaporating, although I think evaporating is technically from a liquid to a gas. Anyway, the ices sublimate and form this diffuse region around the nucleus that has dust and gas. The dust comes off because the ice has glued the rocks and the dust together, but as the ices sublimate, all these little rocks and dust particles become free to sort of just wander around the nucleus. But they don't just wander around in a random direction. They feel the solar radiation pressure, the pressure of the actual photons, and also the pressure of the solar wind. Particles, charged particles that come streaming from the sun. And indeed, here's a video from SOHO, the Solar and Heliospheric Observatory, where an occulting disk blocks the bright photosphere of the sun, and then some, the inner corona as well. But you can see the solar wind coming out, and you see these coronal mass ejections and things, and they can be wonderful at producing auroras and stuff, and we might have quite a number of those in the coming year because the sun is getting near its activity cycle. By the way, here you see two so-called sun-grazing comets heading in, and they might not have made it out. I don't know. Some of them plunge right into the sun. Some of them barely make it around without disintegrating. These may well have disintegrated since I don't see them coming out, but possibly they came out somewhere up there. Anyway, SOHO has found something like 2,000 of these sun-grazing comets, and the main subject of my talks, Comet ISON, is a sun-grazing comet. It will come very, very close to the sun. Anyway, the solar radiation pressure and the solar wind pushes the gases and the dusts away from the comet, and then the dust reflects sunlight, and thus is visible, and the gases sort of fluoresce. Okay, the ions and the atoms also fluoresce, and that causes another tail. I'll show you some tails in a few minutes. Anyway, here's Comet Halley in 85-86, a periodic comet that comes around every 75, 76 years or so. And the Giotto spacecraft went and imaged the thing up close, and you can see that indeed it's this, in this case, peanut-shaped thing, you know, about 10 miles, I think, along its long side and thinner this way. But it's definitely just an icy dirt ball that's kind of exposed to the sun and evaporating. And so initially, the gases and the dust come off in a direction that faces the sun, but then they feel the pressure of the solar wind and the light, and they get swept back to here. But here we can really see that it really is an icy dirt ball. Okay, so when the thing is off out here in the deep freeze of the solar system where it's cold and the ices do not yet sublimate, you don't see a tail, you don't see a cone, you don't see any cloud of gas or dust around this frozen object. But as it comes closer to the sun, it starts developing a tail. And the tail basically points away from the sun, even when the object is in its outbound path. And so there you see that in a sense the tail is leading the head. It's not like I've got super long hair and I'm running hard through the atmosphere, and like Fabio, you know, my hair is kind of being swept back. That's not what's happening in the case of a comet tail. It's not being swept back by the interplanetary medium, the space between the planets, the gas between the planets. Rather, it's being swept back away from the sun by the radiation pressure in the solar wind. Okay? Now, it spends most of its time out here, very little time there. That's because gravity is pulling on it much, much more when it's closer to the sun, and that makes it whip around very quickly. And there's a mathematical formulation of that known as Kepler's second law. Okay, so it just goes whizzing past the sun in the case of a periodic comet like this. Here you can see demonstrated proof that the tail is not following behind the motion of the comet. Here's Comet Hale-Bopp a couple of nights apart, a double exposure, and it moved from here to there, perpendicular to the direction in which the tail is going. Okay? All right, well, the dust particles, as I said, reflect sunlight, and some comets have primarily a dust tail, and McNaught was one such comet. Most of this is the dust, and indeed, it takes on this curved path because once the dust gets blown away, gently blown away from the comet, it's farther away from the sun, so it takes on now a different orbit. It's following Newton's law of motion, and its orbital speed is slower than that of the head, and so it tends to curve back. And indeed, let me go back here a little bit. I deliberately drew these things as curving back a little bit because once the particles are out here, they're farther from the sun, and so they start lagging behind the nucleus a little bit. So you tend to get a curved tail like this. That's this curved tail of Comet Hale-Bopp. It's also this curved tail of Comet McNaught, and it's striated like this because McNaught had many outbursts of dust. This sublimation is not a steady process. It occurs sometimes in bursts. These are cirrus clouds and stuff in Earth's atmosphere, of course. But then there's also what's called the gas tail, or the ion tail. And in a multicolored picture, that tends to appear blue. And it basically is straight away from the sun in, just in a more or less radial direction. It doesn't curve away like this at an angle. And that's because the ions, it's really for two reasons. The ions are following the magnetic field of the sun, which to a good first approximation is radial. Moreover, these ions are not very massive compared to the dust particles, and so they get shot out away from the comet at a much faster speed. So they go zooming away at speeds much faster than the orbital motion, and so there's not much curvature because they're still dominated by outward motion like this, not by their orbital motion. So they don't have a chance to take on this curved path by the time they fade way out here somewhere. That's why you have the ion tail pointing pretty much away from the sun. Now, Hale-Bopp was so beautiful that Patrice Stone, one of our staff employees at the Berkeley Astronomy Department, made this wonderful T-shirt with the Berkeley Campanile and the now defunct Campbell Hall. It's been finally torn down. I've been at Cal for nearly 30 years, and it's been earthquake unsafe my whole time there. And I kept hearing how it's going to get torn down, but I'd been fooled before, and I finally said, they're not going to kick me out, until I see the bulldozers and the wrecking ball coming. Well, 2 summers ago, the bulldozers and the wrecking ball came, and I got out. And it was a split second, of leeway there. I think I was the last person out of the building. Anyway, so that was just a gorgeous comet. Okay. All right. So Comet McNaught had mostly a dust tail. It turns out had a little bit of an ion tail. It's hard to see here. Comet Hyakutake, just a year earlier, at least when it was brightest, had mostly a gas or ion tail. Later on, it started developing a dust tail, but there wasn't much dust, coming off from the nucleus, at least when it was at its brightest and whipping across the sky pretty quickly. And so that's a tail pretty much pointing away from the sun. But most comets have sort of both a dust tail and an ion tail. Like Hale-Bopp was a classic example where you have both of them right here. There, yeah, Hale-Bopp. Dust ion, McNaught mostly dust, Yakutaki mostly ion and gas. All right. Well, where do these things come from? I alluded to this already. They come from the deep freeze of the outer solar system, from one of 2 or 3 general regions. It's 2 or 3 depending on how you count them. The first is the Kuiper Belt, this region of icy dirt balls at and beyond the orbit of Neptune. And indeed, Pluto has been reclassified as a Kuiper Belt object, one of the biggest ones, but certainly not the only big one out there. Mike Brown, my former student, said it's the no ice ball left behind act if we were to classify all of them as planets. So we might as well classify them not as planets, as Kuiper Belt objects, and with that, Pluto has to be demoted. So they come from there, but more importantly, there's farther out, and in a thicker donut, there's what's called the extended disk of the solar system. And a lot of the comets actually come not so much from the Kuiper Belt, but more from this extended disk beyond and fatter than the Kuiper Belt. You can think of it as a donut or a torus surrounding the Kuiper Belt. So it's either 1 or 2 regions, depending on how you count those 2 or 1. And so those are the comets that come in, roughly speaking, along the plane of the solar system. But it was noticed long ago that there are many, many comets that come in, we think, for the first time from pretty much random directions. So Jan Oort predicted, OORT, a famous Dutch astronomer, predicted that there's a cloud, a vast cloud, extending out to maybe even a light year from Earth, of comets in a roughly spherically symmetric distribution. There might be some substructure here, but there could be 1 trillion of these things out there, mostly kind of just orbiting the sun in a spherical shape. They were ejected out to there by Jupiter primarily, and to some degree the other giant planets once they had formed. So they were ejected along highly eccentric trajectories, but then random perturbations with other stars tend to circularize the orbits. So now it's mostly the sphere, but occasionally they gravitationally nudge one another, sending them either out of the solar system or toward the sun. Or a star. A passing star might have a gravitational influence, nudging them either out of the solar system or toward the sun. And so when they come toward the sun, they very, very gradually speed up until they're very near the sun, and then they speed up a lot, and then whip around and come back out here. And either never to be seen again, or possibly perturbed by Saturn or Jupiter into an orbital period of a few thousand years instead of, millions of years, or maybe even a couple of 100 years. It just depends on how much the other planets perturb them. Now, the Oort cloud is correctly named after Jan Oort. He predicted it. The Kuiper Belt, in my opinion, is incorrectly named after another Dutch astronomer, Gerard Kuiper, who argued that there are very few objects out there, having studied the distribution of incoming comets and stuff. I guess at that time, it wasn't recognized that there were that many more coming nearly in the plane of the solar system compared to all other directions, and so I think he argued that there are very few objects out there. Now, tons of objects have been found, and it's called the Kuiper Belt but he predicted that it's not there. So that just doesn't seem quite fair to me, but whatever. Sometimes when you talk about something, you say it's not there, it'll still be named after you. Okay, so that's the second or third major region from which comets come. And the importance of comets is the following. I mean, they're pretty to look at and all that kind of stuff, but the scientific importance is the following. They are coming from regions of the solar system to which they were expelled early, very, very early in the history of the formation of our solar system. Okay? They've been untouched since then. They were never incorporated into a planet-sized object or even a big moon. They never got differentiated. By that I mean not taking dy dx, but rather in a molten body like the Earth was when it was young. The dense things sank to the center. Okay, so that we have an iron, nickel-rich core, and then a mantle, of silicates and things like that, and a crust. They came from bodies that never experienced that. Even the asteroids cannot be said to be as primitive as the comets because asteroids clearly came from one or more differentiated bodies, at least many of them did, because you find iron and nickel-rich asteroids. I mean, I have one in my office. It's really heavy. It's mostly iron and nickel. Then you have the stony ones and the stony iron ones and the carbonaceous chondrites and stuff. You have different kinds that clearly didn't just, you didn't just have a lump of iron and nickel forming for no reason. No, that used to be the core of a pretty big thing in the asteroid belt that smashed into some other pretty big thing, and millions of pieces flew off. So the asteroids aren't even as primitive. Whereas the Oort cloud objects, and to some degree also to a pretty great degree, the Kuiper belt and extended disk objects are really pretty primitive material from essentially 4.6 billion years ago. And so by studying this material, we can gain some clues to the formation of our solar system and the origin of the solar system, and maybe even of life on Earth, because some of these comets even have some pretty complex compounds in them, and they crashed into the Earth. They may have given much of the water on Earth, blah, blah, blah. Anyway, so they're very interesting things, and they're primitive material. That's the scientific interest, I would say. If you ask the astronomers in this room, they would, I think, largely agree with me. Okay, Comet ISON. Wow. First of all, more properly, comet, but in particular thought to be coming in from the Oort cloud for the first time. Otherwise, if it were a periodic comet like Halley, there would be a P here. Comet 2012, discovered in 2012, S1. Well, it was discovered in September, but that's not what the S stands for. It was the first comet discovered in the second half of September. And S designates the second half of September. A is the first half of January, B is the second half of January, C is the first half of February, D is the second half of February, and so on. When I did this on my drive down, I either miscounted while trying to pay attention to the traffic, or there may be a letter missing, because the second half of September does not quite correspond with S. Rick, do you?
There's no I.
There's no I. I knew that there had to be a mistake. There's no I. To compensate, I have two I's, you see, but anyway, there's no I. And is that because it's easily confused with a 1 or something? Yeah, it's like Fortran, isn't there? There's no IJ. It's been 20 years since I programmed Fortran. What letters are missing in Fortran? There's no programming language. Anyway, whatever. Okay, so there's no I, yes, because I calculated the disk corresponds to the first half of September, yet it was found on September 21st. And so, thank you, Rick. I did come to the right conclusion. I even figured maybe there's no I, J, or K, because there's some programming way, or there's some variable stars don't have I's, I think, either. Okay, whatever. All right, so, ISON. Well, that actually stands for International Scientific Optical Network, ISON. It's as far as I can tell, run by amateur astronomers, but they're doing professional quality work. And, this is yet another example of many, many, many in astronomy, unlike other fields of science, where there can really be a pro-am collaboration. Amateur astronomers make really many professional grade contributions to the field. They're only amateurs in the sense that they're not being paid to do it the way I am paid to count galaxies. It's a pretty cushy job. They need to sit around and count galaxies. But anyway, but these guys are doing really important stuff. They're scanning the skies for potential Earth-bound asteroids. And of course, if we find them decades in advance, then maybe clever applied physicists and engineers could find a way to deflect them. So two Russian guys, Filippenko and Astronomical, found this particular one using a 16-inch telescope near Kislovodsk. And this actually means sour water, Kislovodsk. I wouldn't want to live in a town named for its sour water. Okay? But they're part of this network. And so you might wonder, why isn't the comet named Nevsky-Novichnok? Well, the problem is the following. When they first identified it, it looks pretty compact, like a star. So they could not tell whether this was comet-like or asteroid-like. They weren't sure. They just reported they had spotted something new. They have a very large pixel scale and stuff. And it turns out the next day, other people confirmed it and showed that it was almost certainly a comet. And so in a sense, a number of people contributed to the discovery and the classification. And so they got robbed of the name as a result. You know, I mean, they discovered it, they just, you know, were being honest, and they weren't sure whether it's an asteroid or a comet or whatever. But as a result, they kind of got robbed of the name. And, all right, so they missed out on a little bit of glory. But more importantly, this ISON network is going to find lots of comets in the future if they keep on going. I mean, Shoemaker-Levy had at least 9. Remember the famous Shoemaker-Levy, Shoemaker-Levy 9? That's the way I think we should call it, but whatever. So presumably once they find more of them, this one will be renamed ISON 1. Or maybe all the others will be 2, 3, 4, and ISON, the ISON, will simply be understood as being the first one, okay? But it's an unfortunate name because, you know, it's not named after them and it's not the first one. Whatever. Okay, so there it is. In fact, this is their discovery image, and you might say, well, gee whiz, you know, this is a pretty pathetic looking thing. Why did people almost immediately get really excited? This is now the end of September. There were newspaper headlines almost right away. The reason people were excited is that this thing is still beyond Jupiter's orbit. It's way out there. It was found at, I don't know, 6.6 or 6.8 astronomical units, something like that. And although it was 100,000 times fainter than can be seen with the naked eye, that's already really bright for a comet at such a great distance. You know, most of them don't reach that brightness until they're much closer. So this already indicated that this thing is either very big or for some reason very active. You know, something is just sublimating the gases when they're out of that deep freeze, or maybe more highly reflective than the typical comet, or some combination of those two things, okay? Those three things. But the simplest interpretation is that it's big, and so it's reflecting a lot of light, okay? So then, you know, people looked at the trajectory. By the way, once they discovered it, a number of surveys like Pan-STARRS and some others found it. They found pre-discovery images of it. And so from that, a trajectory could be calculated nearly immediately, all right? So the trajectory was calculated, and it was found that on Thanksgiving Day, November 28th, this thing is going to pass just a smidgen outside the sun's photosphere. The surface, of course, the sun has no solid surface, but it's simply the region beyond which the gases become opaque, okay? It's going to pass less than 1 solar diameter from the surface, quote unquote, of the sun. So it's a sun-grazing comet, or nearly so. I mean, there might be some formal definition, maybe it's within 1 solar radius or something, but it's essentially a sun-grazing comet. And so if it's so big, and it's going to get close to the sun, that means it'll sublimate like crazy, releasing lots of dust and rocks and gas, and it should brighten to a tremendous amount, all right? And so it might become really, really bright. And the headlines that came out, and these were actually inspired in part by astronomers, unfortunately. New comet might blaze brighter than the full moon. Well, that's technically true. It might. Anything might. I mean, an asteroid might hit you right now, but whatever. It's more might than even that. But let me talk about that in a second. Right? This is, you can see 25th of September. Only a couple of days have gone by since the discovery and confirmation of this thing. All right? Brighter than the full moon. And then newly spotted comet may outshine the full moon. And here it is, you know. So, and then, you know, you get things like this massive comet. This Thanksgiving. So I start getting all these comments from people, you know, brighter than the full moon, the thing's going to be blazing across the sky and stuff. Well, yeah. When it's right next to the sun, the evaporation rate is going to go crazy. The solar to comet distance will be small, and so it'll reflect a lot of sunlight, and the distance from the Earth will be roughly the distance to the sun. Okay, that doesn't change very much. So it may be as bright as the full moon. By the way, the estimates have been revised downwards since then. But this is September. It hasn't brightened as much. I'll get to that. But back then, they were going based on what they thought. My complaint is, yes, as bright as the full moon, but at that moment in time, it's going to be in the direction of the sun. It's going to be like a degree away at best. And so, if you're really good and you don't care about your eyes, you might block it out, like I'm blocking that light bulb there, and if I miss a little bit, then I go blind. Well, I mean, it's not that quick. Hopefully you will know that you're missing and you turn away. We've all looked at the sun for split seconds, going around a curve suddenly onto a highway or something, and there's the sun. Few of us are blind because of that. So a split second doesn't hurt you, okay? But you don't want to stare at it, and many people who don't know what they're doing might accidentally stare at the sun. For the same reason this becomes dangerous as during an eclipse. There's a reason for them to look at the sun, and it's not that the sun is more dangerous intrinsically during an eclipse, but it has a greater attraction. People look at it, and there are no pain receptacles in your eye. Or I should say, once you start feeling pain, it means your eye has been fried, okay? And so it's too late. And so that's the real danger, okay? It's not going to be some blazing thing in the middle of the night. And the brightness is going to rapidly decline. I'll show you models in a few minutes, from full moon to maybe Venus or something when it starts creeping away from the sun. So it was just completely misleading to have such headlines, okay? The really astute observer who really knows what they're doing, is very careful, may well indeed see this in the daytime. It'll be interesting to see. Heidi and Isaac, I trust you guys to take care of your eyes. You saw McNaught, I have your picture coming up. But be very careful, okay? Don't expect something in the dark night sky that's brighter than the full moon. So those headlines were very misleading. The other misleading headline was the comet of the century. Here's brighter than the full moon again, right? Should be uppercase, but whatever. All right, anyway, and this guy's pretty knowledgeable, actually. The guy who writes for this event here. So this is a previous comment. It just shows what it might look like, and then in Time magazine, well, at least Michael Lemonic had a question mark here. But this is now December, where people were beginning to have their doubts, okay, about this century stuff, okay? He has some errors in this article, which is kind of interesting because he's a pretty good science writer. But anyway, so why the comet of the century? And why do we now think that maybe not the comet of the century? Here's the point. Okay, so it's supposed to evaporate a lot next to the sun. Solar radiation pressure is spewing all this stuff out. It's reflecting light. Could be the comet of the century. Okay, fine. But there's room for doubt, and indeed, the next few months after the discovery started casting some doubt. And the doubt is the following. If a comet is coming in from the Oort cloud for the very first time, as this one is, we can tell from the orbital, from the eccentricity, it's an extremely eccentric ellipse, okay? It may well have a layer of volatile ices on its outer surface. Ices are not just H2O, water. There's methane, ammonia, carbon dioxide. There are all kinds of things that astronomers call ices. And they have different sublimation temperatures, okay? Water is actually more difficult to sublimate than some of them. And if the thing has been in the deep freeze forever, for 4.6 billion years, and it's coming in for the first time, this outer layer of volatiles has not yet been evaporated away. And we know from previous studies of comets that ones coming in from the Oort cloud for the very first time often have a thin layer of volatiles. And so maybe out at Jupiter and then, closer in, it was getting rid of all that stuff through outgassing. But that isn't necessarily going to be representative of the growth of outgassing as it gets closer and closer to the sun, right? That's the early burst, which won't necessarily be representative of what comes later on. What if the thing is a hard rock? What if it's essentially an asteroid with a thin layer of these volatiles? I mean, it probably isn't. There's no way to easily form asteroids that then get kicked out by Jupiter out there. But the point is, it could be a mostly rocky composition without much other stuff, without much dust and stuff. And so you just don't know. The early brightening, back when it was found, magnitude 18.8 at 6 or 7 astronomical units, could have simply been this early timeout guessing. And so people started tempering their predictions of just how bright it'll be, and very few knowledgeable people at this point say that it's likely to be the comet of the century. But I'll give you my predictions in a few minutes, okay? Nevertheless, people, start following it, and it's easily within amateur telescopes, at least if you have a CCD and take some long exposures or stack together a bunch of short exposures. So here's a nice picture of it. It's developing a coma and a little bit of a tail, and this was taken back in March. So it is brighter than most comets are out there. It's not like I'm not totally excited. I'm somewhat excited, but probably not comet of the century. The SWIFT satellite took some data on January 30th, and from the amount of outgassing, you can do an analysis and figure out an approximate size. And it's about 3 miles in diameter, which is not as big as, say, Halley's Comet. Hale-Bopp was of order 30 miles, I think, but Hale-Bopp didn't come as close to the sun. So 3-mile diameter comet coming this close to the sun is still something to be excited about, all right? I'll show you Lovejoy in a few minutes, which was 1/10 of the size of Comet ISON, and it put on a beautiful display in 2011 if you were in the southern hemisphere. So this is nothing to sneeze at, but it's not like it's some gigantically humongous comet passing within 1 solar diameter of the sun's surface. Okay? Hubble pictures of it later were analyzed, and they come up with about the same diameter. It appears to be about 3 miles, 5 kilometers, something like that. Pretty typical for a comet, but atypically close to the sun, which is why it might brighten and sport a very long tail. I mentioned Comet Lovejoy 2011. It was a considerably smaller sun grazer, and it became a very, very nice comet. Here's a picture from the very large telescope system in the Andes Mountains of Chile, Paranal. Beautiful comet. There's a Magellanic Cloud right there. There's maybe the other one there. Anyway, so could be really good. Well, so what's it been doing? Well, the problem is we don't know. Because right now, it's 5 degrees away from the direction of the sun. And so it's been hard to follow. Here's what? December 2012, January, people were monitoring it. Here's the SWIFT observation, January, February, March, April, okay, May. So, okay, now it starts getting into Gemini, and Gemini at this time of the year is basically in the direction of the sun. So the point is, starting early May, I believe, late April or early May, I think it was, for most telescopes it became too close to the sun to monitor. And so we don't know what it's been doing. We will get an update sometime in August, certainly by early September. You should be able to see it in your small telescopes again. And some of you might be able to see it sometime in August. So everyone's waiting to see how much it has brightened, okay? We'll see. But right now, we just don't know. By the way, on October 1st, when it's just crossing into Leo, it's going to pass within 7 million miles of Mars. And so here's a simulated photo by the Curiosity rover. This will be the first picture ever taken, either by Curiosity or maybe one of the orbiting satellites of Mars. But NASA plans to take at least one picture of Comet ISON from Mars. This will be the first picture of a comet ever from another planet, at least by humans. I don't know about the Martians, okay? So here's a simulated view of what it might look like, and that'll be like totally groovy, seeing a picture of a comet taken from Mars. How do you like that, okay? All right, so let me just go back to this one. October 1st, October 15th. You see, by the way, it's speeding up. It's speeding up. It was just kind of cruising along, but it's getting closer to the sun, so it's speeding up. Kepler's second law. By November 1st, 17th, it's off here in Virgo, I think. And here is a simulated view, simulated from Earth, November 17th, about an hour before sunrise, okay? So, if we're lucky, it will already begin to sport a pretty nice tail. I mean, it already has a little bit of a tail. But if we're lucky, it will have a sizable tail. Although I will argue that by far the biggest tail should be after it passes perihelion and it's closest to the sun. So, starting November, start getting up in the morning and monitoring its progress. Or do what I did with Comet West in 1976 and don't pay any attention to it until right around when it's supposed to be the best, and then go out to the eastern and look at the eastern sky and be totally blown away. I'll tell you this. Well, I already kind of told the story. December 10th or so, or 8th or 11th, when it should be at its best. But if we're lucky, it'll start doing this, okay? Then, take a look at this. All right, Kepler's second law in action. November 27th, 28th and a half, let's say, 30th. Zoom, they just go zipping by the sun. Yeah, right here, folks, it'll be maybe the brightness of the full moon. We're over here. That's not good. But by the time it's over here, its brightness will have plummeted. And that's what the newspaper articles did not tell you, at least not initially. And even the astronomers who were excited, I think they misled some of the reporters. The reporters were misled. The astronomers said that it would be the brightness of the full moon, though technically true, perhaps, highly misleading. Okay, so then what happens, right? So here's the thing. It's evaporating like crazy here, tail's being pushed back, comes out, more outgassing is occurring, So this is where we might see a very nice show. And I'll show you why in a minute here, courtesy of Sky and Telescope magazine is a nice little set of pictures of what it might look like. Okay, so November 28th, 28 and a half, something like that, as close as to approach. You're not going to see it unless you're very careful. By December 1st, it may emerge in the morning sky, but there's a competition here between at least two effects. With every increasing day, it's higher above the horizon and farther away from sunlight, okay, from twilight. On the other hand, it's getting farther away from the sun, so the amount of reflection and outgassing and all that is decreasing, okay? And inverse square law of light is starting to hurt you. Even if it's got a lot of stuff in the tail, it's getting farther away from the sun, and so less light is reaching it and bouncing off. All right, but it is getting higher into the sky, into a darker sky. So somewhere around December 5th to 15th, I think. I'm not a comet expert. I study black holes and supernovae and the expanding universe. So this is just based on what my buddies tell me. And by the way, they're the ones who told me that it would be the brightness of the full moon. Somewhere around December 10th and 11th might be the sweet spot. But if you check the weather patterns of where you're living, if it's going to be cloudy, then by all means get up earlier than that. Many of you, like Heidi and Isaac and others, will want to follow it day by day. I tend to stay up late at night, and I have a hard time getting up in the morning. But I think I'll try and get my kids up and stuff. This is 30 minutes before sunrise, all right? There's the moon on December 1st. Should be a very nice, very pretty kind of pair. There's Mercury, by the way. Not many people have seen Mercury. Here's a simulation in December. December 1st, 5th, 10th. 10th, that's looking pretty nice. This is just simulations, right? We really don't know. Let's look at the geometry. December 11th, that's what some people think will be the best morning before sunrise. Here's what's going on. Here's the Earth, there's ISON, and the tail is going to be pointing roughly like this. So we're roughly perpendicular. This is what you want. You don't want to be looking along the tail, a foreshortened view. That was the problem with Halley's comet. Some people say astronomers predicted that Halley would be really bright end of 85, beginning of 86. No. We knew what the geometry would be. It's not a favorable apparition. Neither is the next one, for which I plan to be around. And the one after that is going to be a good one again. Kind of like 1910. I don't remember 1910 very well. I was pretty young at the time. Anyway, no one said that 85, 88, well, maybe some people did, but they were wrong. Anyway, this is the right geometry, roughly perpendicular. So all the things are kind of coming together. It's pretty big. So there's a lot to evaporate. It's getting close to the sun, so it could evaporate a lot if it doesn't get destroyed. That in a minute. And then it's coming out here. Tail should be pretty bright, and we're perpendicular to it. Okay. As it gets farther out here, well, it's getting farther from the sun. The reflection is going down, and we're starting to get more of a foreshortened view. Okay. Anyway, so December 11th. All right. Here's a simulation I found for December 10th. Hey, December 11th, plus or minus 1 or 2 days, So here's December 10th. Here's what someone thinks it might look like. But notice they've only shown a straight eye on our gas tail. Who knows what the dust tail will look like? Comet McNaught, oh my goodness, I wish I lived in the southern hemisphere. It had this amazing thing curving away. So that's just someone's guess, all right? We know exactly what the trajectory is. We just don't know what comets will look like, okay? All right, what did I have here? Yeah, closest approach to the Earth, by the way, will be December 26th. 39 million miles. No danger, okay? It poses no danger to us, all right? Second half of December, what's it going to do? It's going to fade, but it's going to head north. And you can look up, for example, if you Google, Comet ISON ephemeris or something like that, you'll find sites that have this. Here's one that I found the other day. It'll eventually become visible all night. It'll become circumpolar, as seen from most of the U.S., okay? At least from mid-northern latitudes. It'll head, in fact, toward Polaris. It'll be pretty close to Polaris. So here it is coming in, coming in, coming in. There's perihelion. It's whipping around the sun, goes zooming up like this through Ophiuchus, Hercules, Corona Borealis. That's getting pretty far north. On into Draco. Oh my goodness, that's really far north. Into Ursa Minor. Well, gee whiz, the Polaris is the end star of the handle. And then it cruises over to here. Okay, so it'll be circumpolar near the end of sort of maybe the last third of December. Depends on, of course, what latitude you live at. But circumpolar from the whole U.S. by the end of December and into January. Okay. By then, it should be still visible with binoculars and small telescopes. By the way, when it's bright and stuff, early December, naked eye will be great, but if you want to see fine structure near the nucleus in the tail, by all means use binoculars, a telescope, whatever. But if you don't know any of those things, don't worry, be happy, naked eye will be just fine. But how bright will it be at its best, okay? All right, so let me show you this little plot. Here's the apparent magnitude. 6 is, roughly speaking, the limit of the eye, the unaided human eye in a nice dark area, okay? And this is for the nucleus. This doesn't really account for all the integrated brightness of all the dust in the tail and stuff. People here are talking about the nucleus. So this is what gave people pause here. It kind of slowed down. It really didn't brighten after the initial detection, which was brighter than it should have been, in a sense, at that distance. Then it brightened, but then it stopped kind of brightening. And this is some sort of a model. I'm not sure what it is. They don't even show the couple of hours near peak here because it's all, it's totally model dependent and stuff. This gets cut off. The resolution isn't good enough to see what's going on in the one day when it's passing close to the sun. Maybe it'll reach minus 13 or 12, which is what the full moon is, but the best estimates now seem to be like minus 5 or so, which means it'll be somewhat brighter than Venus, the nucleus, but again, in the direction of the sun. Now, a lot of you have seen Venus during the day. I've seen it many times, but it takes some effort to see Venus during the day, okay? And moreover, all of Venus's light is concentrated into a little tiny dot, whereas here the light is spread out, so it might be tougher to see than Venus, and it'll be closer to the sun. So it'll be an interesting challenge to look at it during the day here, but be very, very careful. Anyway, what's it going to do when it should be sporting a tail? Well, the problem is this. There are many, many variables. One big issue, this is a real possibility, is that it'll be completely destroyed by the sun at or near perihelion. It'll sublimate away so much, and all the stuff will get so destroyed and so dispersed that there'll be very little to see. I mean, you might say, well, gee, if it's really dispersed, then it'll be a big fat tail. But if there's too little material per unit area in the sky, then yes, the tail might technically be there, but there's nothing much to see. You want the dust to be kind of concentrated. So you don't want it to be completely destroyed. I mean, we don't think it's going to actually be eaten by the sun, because it's going to pass one solar diameter or a bit less from the surface, but it's still going to be in the region where there's strong radiation pressure. If there's some big coronal mass ejection or some solar flare, that could just completely destroy the thing before it has a chance to form a nice tail. Composition. Different ices, so everything that I said kind of depends on it not being destroyed. And there's a significant chance it will be destroyed. But Comet Lovejoy's was 1/10 of the size and was a sun grazer, and it didn't get destroyed. So, whatever. Composition, different ices, dust, and volatility. Well, if it doesn't have much dust, it won't have much of a dust tail. Well, Hyakutake, Mike Ham, my friend, remembers that. I even showed you a photo. I might even have it here somewhere. It had a nice ion tail, but a lot of people like to see the dust tail, like from Hale-Bopp. That depends on composition and stuff. How much of the dust will be released after more of the ice is supplement, The thing is sort of slowed down here. Nothing much more is being released here. It's flat. If it were continued, that would be really boring, okay? Now, it's not going to continue that now. It's sit around there. Will it break apart into several pieces? This could be good. Destroying it completely, obliterating it would be bad, but breaking it up into a few pieces would be good, because then there's more surface area over which ices are sublimating and dust is being released and more stuff is coming out. A great example of this was periodic comet Holmes, which is usually a pretty crummy comet. No one ever pays attention to it. It's periodic. You can see it pretty much all the time, but it's really faint. Almost overnight, on October 23rd, 2007, it brightened by a factor of 1 million. How many of you remember this? Comet Holmes suddenly becoming this naked eye thing, It's because it just had some kind of a weird breakup, some ejection. There was gases sublimating inside it, and like in a pressure cooker, they were getting blocked. Maybe there was no easy passage for them to escape. And then finally it just blew, and it emitted this coma of stuff. This is mostly dust. The blue stuff is gas, it's ions. The rest is dust. That's what contributed to its brightness, and it became a great comet. I mean, totally unanticipated. So if ISON does that, then we're golden. Then it could well be the comet of the century, right? Here's one, Comet Linear, 1999. It broke up into a bunch of pieces, and Shoemaker-Levy 9 broke up into a bunch of pieces because of the tidal forces of Jupiter, not the sun, but Jupiter, So there are a lot of variables, and forgive us if we can't tell you exactly what it's going to look like. We can tell you where it's going to go, and where it would go if it survives perihelion passage, which it might not, by the way. But up to then, we can tell you precisely its path, but we can't tell you what it will look like. And David Levy, famous comet hunter, has this wonderful quote: "Comets are like cats. They have tails. They do precisely what they want." So we just don't know. And looking at the audience here, quite a few of you are my age, or a little bit younger, or a little bit older. Comet Comet. How many of you remember it? 73, 74, okay? Comet of the century. Not. Anyway, there's a picture. It wasn't bad compared to the run-of-the-mill comet. Run-of-the-mill comets are fainter than this. I mean, you could see it with the naked eye. Mike Hanna and I were in high school. We watched it. I think I was president of the science club or something. We almost got lynched for bringing all these students out there, and we could barely see it from the football field. Maybe not because of the stadium lights, but whatever. So it was there, but the point is there was so much ballyhoo about this comet. They called it the comet of the century, the great comet, every adjective you can think of, and it fizzled. I'm not exactly sure why. I think some of it disintegrated away earlier than perihelion passage or something. Like I said, this is not my research field. I haven't looked into it, but it was simply not what it was predicted to be, and so in the public eye, it was a complete failure. It was a complete dud, and indeed, often people now use the word Kohoutek as not that we have anything against the Czech astronomer who discovered it, but it means kind of a fizzler, a dud of a comet. A Kohoutek kind of comet, By the way, there were all kinds of great headlines. The comet, Kohoutek, the world's most spectacular new comet has arrived. Is it a messenger of doom from outer space, or a scientific clue to the birth of our universe? Anyway, so the greatest hard signature of all time. Okay. So what's my prediction as a non-expert, but reading some of the literature and looking at the behavior of some previous comets, including ones in my own lifetime? I think Comet ISON will be the best comet visible in dark skies in the northern hemisphere since Comet Hyakutake in 96 and Hale-Bopp in 97. Okay, so here's Hale-Bopp, here's Hyakutake, they were darn good. We've had a long dry spell. 16 years, Hale-Bopp, 17 years, Hyakutake. If ISON ends up being as good as they are, then, fantastic, okay? Not the comet of the century, but a real nice comet. Sure will be better than Pan-STARRS, which was a bit of a dud, if you'll remember back in March. Yeah, I barely saw it. I brought a bunch of my 800 students out. They're all home. I had to tell them this is brighter than we've had in the northern hemisphere for quite some time. Holmes was there, but it was more or less round. You had to know where to look, and whatever. It was an amazing comet, but not super bright from the public perspective. You know, maybe it'll become as bright as a KSEC. I mean, that would be fantastic. I mean, you know, possibly the best one of the 20th century, depending on with who we speak. The reason I say northern hemisphere is that the southern hemisphere has had 2 good comets in recent years. Lovejoy, 2011, look at that, nice comet. And then McNaught, you know, which I've shown a number of times, you know. But in the northern hemisphere, we've been underprivileged. Now, Heidi and Isaac and some others did see McNaught in heavy twilight. You know, it was visible for a few short days from the northern hemisphere, but then it quickly dipped into the southern hemisphere. But this is in bright twilight. You have to know precisely where to look. It's not the kind of thing where you tell your neighbor, hey, just go outside, look, and you know, you got to be blind not to see the thing. Kind of like Hale Bob. If you made any attempt whatsoever to go to a reasonably dark site, it was just so obvious, you know, right? So, you know, McNaught was visible. In fact, it was even detected in the daytime by really astute observers, but it was not a good northern hemisphere comet, okay? But it turned into this thing. I mean, you know. So if ISON becomes like McNaught, but for the northern hemisphere, hey, I'll be happy, even if it isn't quite the comet of the century, you know. Definitely observe it, either monitor it day by day if you wish, or go out, you know, don't follow the news and stuff. Just go out one morning in this interval, something like this, or December 8th or 14th, if this is predicted to be cloudy. And it might be like my Comet West experience. I was a freshman in college, 75, 76, and I had heard about this comet, but I was really busy studying. I was the quintessential nerd. And it was a morning object, so it wasn't, you know, easy for a night owl like me to see, because it was really, you know, like 4 or 5 in the morning early, not 1 or 2, which would have been fine with me. Anyway, one day, I just decided I'm going to get up, and I'm going to see this thing. And I was in my parents' house. I think it was March of 76. Went outside. I looked toward the east, and you know, this is not my picture, but I saw this amazing thing going from nearly the horizon upwards with the tail merging or beginning to merge with the Milky Way above it. It just blew me away. And in part because I didn't know what to expect. I was busy studying, I hadn't watched it, I hadn't followed the news, the internet had not yet been invented, okay? Al Gore was a young tyke and whatever. And so, by the way, whatever. So, and he never said that he invented it, but he did say something. So it was spectacular from that perspective. Okay, now it's much harder to be completely oblivious of the news. But it was an amazing experience. I woke up my parents, and they were actually even glad that I woke them up, you know, at 5 in the morning to see this thing hovering over the eastern horizon. And then, you know, and this is what this whole conference is all about, use it as an opportunity to excite our youth, you know, to stimulate interest in science and, you know, in adults as well, but youngsters in particular, because they're the next generation of future leaders. And, you know, I have nothing against Asia and other countries booming up in science and technology, but I would like the US to remain in the upper echelon as well. And we are being, I'm sorry to say, left behind at this rate, okay? So this is a great chance for STEM outreach, organized comet viewing parties and stuff. I'm a bit bummed that it's going to be best when it's an early morning object and not an evening object. Those are simply the breaks. You're going to have to make an effort to get people up to see it. But in the second half of December, hopefully it'll still be, or especially in the final third of December, I'm hoping it'll still be pretty bright, and then it'll move into the evening skies as well. And as I said, it'll be circumpolar. So, you know, organize comet viewing parties, but use this as a chance to stimulate interest. And there are other opportunities of this sort. You know, the Perseid meteor shower, which is an annual thing, partial and total solar eclipses. There's a total solar eclipse coming up in 2017. That'll be a great opportunity. So there are other such opportunities, but here's a gift of the greatest northern hemisphere comet since 1997, and we should make use of that gift. There's been, of course, other chances of STEM outreach recently, and in particular, you know, we all know Saturn, and just a couple of days ago, there was the whole Wave at Saturn campaign that NASA/JPL organized. And that's because they were taking a picture of Saturn, and this one was actually taken in 2006. It's a backlit picture, which means that Saturn's basically eclipsing the sun, So you see some sunlight filtering through the outer atmosphere, and you see the forward scattering from the disk, which means, from the rings, which means you can see really faint rings and stuff, because forward scattering is a very efficient process, okay? So it was scientifically very interesting. There are all these weird striations and stuff. But right here is Earth photobombing the planet Saturn's photo. Here's Saturn posing for a photo, and Earth photobombs it, okay? What is this, you know? Anyway, back then they didn't make a big deal out of this. Actually, eventually they said, hey, there's Earth, it occupies 1 pixel and stuff. But this year, Carolyn Porco, the principal investigator of the Cassini mission, and she was a classmate of mine at Caltech when we were graduate students, she has made a big deal of this because another opportunity came up when a photograph of Saturn was being taken and Earth happened to be photobombing it there, or at least in a position to photobomb it right there, okay? This is really very rare. I mean, it's a small field of view. They're only looking at Saturn. Usually Saturn and Earth are not collinear with the sun, you know, and blah, blah, blah. So this is a rare thing, you know. So she made a big deal out of it, and it was kind of fun, right? Because here we are in North America, and this is at the time the photo would have been taken. By the way, we all had to wait 80 minutes and 3 seconds before the photo was actually taken, because it takes that long for light from Saturn to reach us, or for light from us to reach Saturn. So if we are to be waving at it at the right time, we had to do it 80 minutes and 3 seconds earlier. But whatever. It was around 2:30 p.m. here in California. And you know, we're just barely above the, well, it was near our horizon. Saturn was very low in the sky. I'm not sure if people waved in the right place. Most people waved too high up. But whatever. If you're just waving at the sky, that's fine. You know, you're in that picture. Maybe. I don't want to throw water on all this and stuff, but it turns out that the odds of one of your photons actually being are very, very low. I forgot what the thing is. There was a Sky and Tel article about this. It's like 1 in a million of us maybe had a photon that actually registered in that photograph. But it doesn't matter. It's the principle of the thing. Everyone's waving, and they might be in that picture. They're in the field of view. Who cares whether a photon really did reach the detector after being reflected from you, okay? So here are all the various employees at JPL, and I love this, right? The rings of Saturn. And I waved at Saturn, and I got a certificate, so there we go. There's a little thing, you can just Google it. You just type in your name, and they email you one of these certificates. I think where I was, I didn't have a clear eastern horizon. There was a kind of a mountain and some trees in my way, but I kind of just, waved anyway. So no photons from me got there for sure. My kids might have a better chance. They're waving, although I'm not sure. Noel, is this building due east or southeast? Maybe it was blocking, whatever, Anyway, but that's a good chance to get kids excited. It's not scientifically significant, but it was still a fun thing to do, to generate interest and stuff, okay? And then finally, I do want to leave some time for questions, but let me do this very quickly. What is today's date? Everyone knows today's date. July 22nd. Okay, well, 22 over 7, 7 being July, is about 3.14. So this is known as pi approximation day. Because indeed, do it on your iPhone or whatever, your BlackBerry, 22 over 7 is, those are the first 3 digits, and you don't even have to round, okay? That's what they are. Pi approximation day. And indeed, either deliberately or not, in the logo for, there it is. Okay. Jim, was that deliberate? Absolutely. Of course, the conference spans pi approximation day plus or minus a couple, but I'm speaking on pi approximation day. Now, it's kind of a cute thing, but the bigger deal is the true pi day, which is March 14th, 3.14. And the reason I say it's a bigger deal is that it has been officially recognized by Congress. House of Representatives Resolution 224 in 2009 they said, they proclaimed this to be not a national holiday where you can just skip out on going work and stuff, but rather a day in which schools are supposed to celebrate pi, talk about the interesting properties of pi, do little, eat pie, of course, P-I-E, and do fun activities with kids to get them interested in science and math. Because, of course, we all know that pi appears all over the place in science and engineering. You can learn more about it at Noel's website, pizone.org, Noel's website. Pi is fundamentally the ratio of the circumference to the diameter of a circle. And, it's just area of a circle is pi r squared, volume of a sphere is 4/3 pi r cubed, and of course it goes into higher mathematics in many, many ways. Wave motion, Heisenberg's uncertainty principle, whether the universe will recollapse or expand forever in the absence of dark energy. It turns out the critical density of the universe depends on pi, all kinds of things. The temperature of a black hole, which is made up of a bunch of fundamental constants, it also has pi in it. So it's just all over the place. But a couple of fun things about pi, just to tell you a little bit about it. Expressing it as two integers, m over n, well, 22/7 does pretty well, 3.14. Interestingly, 355 over 113, so there's 113355. That gets it to 6 digits. That's kind of interesting. 113355. Just remember that. Impress your friends. Cocktail party next weekend, thus assuring that you will never be invited to a cocktail party. It's of course an infinite sequence. It never ends. There's no pattern. It's not that it's random. By random we mean just the digits are just kind of thrown out. It's the same sequence of digits each time. It's determined by something. It appears random, but the point is there's no obvious pattern and it does not repeat. And the exact value can never be found, although 10 trillion digits are now known, okay, through various computational programs. Now, you don't need to memorize lots of digits. In fact, there's no real reason to memorizing more than a few. But if you wanted 10, here's one that Noel made up. Wow, I made a short, memorable pi string, could you? So 3 letters, 1 letter, 4 letters, and so on. 3.14159265 okay? So that's kind of interesting. And then someone else, I forgot the author. Here's 24 digits. How I want a drink. Alcoholic, of course, except for those of you under 21. After the heavy lectures involving quantum mechanics, all of thy geometry, Herr Plunk, is fairly hard. So there it is, the 24 digits, okay? I'm not sure why you want to memorize more than that or even that many, but some people make it their life's mission to memorize it. Some Japanese guys memorize like 64,000 digits. It's like, I mean, don't you know better than things to do? But, just the Guinness Book of World Records. A couple of interesting things. John Wallace in the 17th century found that 2 over pi is 1 times 1 over 2 times 2 times 3 times 3 over 4 times 4 times 5 times 5. All the odds in pairs over all the evens in pairs gives you 2 over pi. Interesting mathematical trick, okay? You have to go on forever to get this right, Here's one, James Gregory, also from the 17th century. Pi over 4 is 1 over 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11. You see the pattern there. The odd, every other one, I mean, they're all the odd bits here, but every other one is alternating signs. That's kind of an interesting thing. Archimedes of Syracuse at around 250 BC was the first to calculate pi to any reasonable number of digits. Here's the method he used. Very clever guy, Archimedes. Indeed, this is sometimes known as the Archimedes constant because he was the first to get it reasonably well. You take a circle and inscribe a polygon. Here's a hexagon. Clearly, its circumference is smaller than the circumference of a circle, right? Now circumscribe a hexagon. Its circumference is clearly bigger than the circumference of the circle. So that gives you a lower bound and an upper bound to the value of pi. As you increase the number of segments in your polygon, the straight lines approach but never quite reach the continuous curve, the circle. And you get better and better lower and upper limits to what pi is, because you divide the circumference by the diameter and that gives you pi, by the way. This gives you the circumference, but you then just divide by the diameter. with a 96-sided polygon. Archimedes was able to compute this. You try computing the circumference of a 96-sided polygon. It ain't easy, okay? I don't know of any clear trick to do it. It's not just, and going to your little calculator is not fair. Archimedes did not have an iPhone, okay? So, anyway, he determined that pi is between 3 and 10/71 and 3 and 1/7, okay? Which turns out to be 3.14, okay? So it's called the Archimedes constant. Pi in pop culture, just a few little things. In Carl Sagan's Contact, it turns out the digital sequence of pi is said to contain a hidden message from beings that created the universe and the human race, okay? And moreover, the locker combination that Ellie Arroway has is 314159, okay? If you look at her locker combination, Ellie Arroway, the heroine of the novel. In Star Trek, Spock brings down an evil computer by demanding that it calculate the last digit of pi. And by the way, at my wife's website, ISON.org, I'm not wearing it right now, but she's got a bunch of really cool t-shirts for the geeky among you. My favorite, about which I get so many comments when hiking in the Sierras or whatever, my PIN number is the last 4 digits of pi. Pi is not for square, that's another good one. So pi will be more and more in pop culture because these teachers hopefully will take on the world and we get $1 billion buyers. Pi dollars out of every sale goes to getting a t-shirt or some other pi-related thing to a school teacher. So we're trying to do some good public service there. There's a 1998 Darren Aronofsky movie called Pi. It's about a mathematician who gradually grows insane by trying to find a pattern in the stock market, okay? And it's called Pi. I mean, I don't think the pattern is pi, but whatever. The movie is called Pi. So, now in 2005, Google offered exactly 14159,265 shares of stocks. And so you subtract the 3 and you get that many shares. If they had put a 3 in front of it, that probably would have been too many shares for them to offer, but whatever. And then their logo was this, and you can see some of the things, of course, the area of a circle, wave motion has pi in it. There's 22/7, there's pi approximation there. Actually, no, that's 223/71. That's the Archimedes thing. That's 3 and 1/7, and that's 3 and 10/71, right? So there's the Archimedes constant. All right, and they show the technique he used, and anyway, kind of fun. And then here's a great one, Einstein's birthday, March 14th. So 133 years old on Friday. So Pizone.org is a good place to go for pi-related things. And since all of you have smartphones, I will leave this up for a couple of seconds here. If you want to receive Pi Day updates, okay? Just just take a picture of this QR code here, and you can get on a mailing list, and we will not sell your email address to various porn sites and stuff, or Viagra distributors, or Anyway, so Pi Day updates, if you want such things, okay, for all of you. Everyone got it with your phones. But in general, this is a good way, again, to encourage interest in STEM-related fields, okay? So Pi Day. You can do fun things to illustrate pi and its applicability, and maybe eat some pie, and maybe do some fun things like cut apart a banana and measure the length of the peel that you've peeled off of a little cylindrical part of the banana, and then measure the diameter of the banana and see that the length is roughly 3 times the diameter and stuff. Okay, and then of course, back to the topic of my talk. Although I see, since this is the first time I gave this talk, I ran way over. It's not as polished as my other talks, but whatever. Enjoy Comet ISON. Show friends. Promote astronomy in particular, but of course STEM and science in general. But astronomy has such great public appeal, and you can help introduce this to people, since it's not going to be exactly obvious in the evening sky. You have to tell people to get up in the morning sky, and then show them later in December the comet as well, but it just won't be quite as good then. And then if you want to get astronomy updates, here's a different QR code that you can take a picture of. And again, you'll get on a little emailing list where I hope to develop a system where every once in a while, if something is coming up, I will simply email a little blast saying, hey, did you know about this? Like, I've spoken to a number of people who thought the Saturn wave thing was kind of cute, but simply did not know about it, okay? And I know a lot of people who don't know about Comet ISON yet. Of course, there will be much, much more in the news, but there could be events that come up that I happen to know about. Some supernova exploded just within amateur astronomer telescopes or something like that. That might not be something that you hear about right away, but I'll be happy to email you. So that's it. Thank you for indulging me for so long, and I hope we have some time for questions.
Prehistoric phones get on those lists.
How do those prehistoric phones get on those lists? I don't know. My agent, Noel, needs to answer that question. The question is, how do those who do not have phones get on that list?
I'll take your email again over here.
Yeah. Noel's. You could email.
We're not so social media savvy.
You can email noel.filippenko@gmail.com.
Updates at astroalex.org.
Yeah, there's astroalex.org. Does that email address still work, Noel?
Updates at astroalex.org is what, yeah.
Astroalex.org. Does that email work?
Updates at astroalex.org.
See, I don't even know the password, but you do, so. Okay, so astroalex.org.
Updates.
Or
Updates.
Yeah, okay, good. Sorry about that, we figured everything out. Yes?
You talked about populations of the Oort cloud. How many would you guess are migrating out versus migrating in?
Yeah, population of the Oort cloud. So that's a trillion, and then the question specifically is how many are migrating out versus in? I don't know. My initial reaction would have been that, in a sense, the amount of phase space outwards might be thought of as being bigger than the amount of phase space inwards. But I'm not sure about that, because if you think of the sun here, and here's a comet going along essentially a circular orbit. It's got almost zero energy. A bound orbit technically has negative energy, but one that's way out there, that's barely bound, has what is nearly zero energy. Indeed, when you come in with a parabolic orbit, you're coming in as though you were dropped from rest at infinity. That's a zero energy orbit, okay? So if you were to disturb it a little bit inward, even if it's the slightest bit, I think that would make it come in toward the sun, whereas outward make it go away. So maybe it's roughly equal. Does anyone who's more of a comet expert than I am know a more definitive answer to that? Rick? I don't know. Yeah, not sure. Good question. Let's say 50-50 for now, but one of them or the other might actually be more. I could be a politician. There was a question right behind you, I thought. No? Or was it two hands sticking up just by notice? Yes, right there.
In viewing a comet, would it be advantageous to use a filter, like a light?
When viewing a comet, is it advantageous to use a filter? So some of you have, for example, narrowband filters with which you can see the ring nebula really nicely. And the reason for that is that the ring nebula is an emission nebula that has these emission lines that are only at specific wavelengths, and if you blot out all the other wavelengths, you decrease your sky brightness while not decreasing your nebula brightness, and that increases the contrast. So for the dust tail, definitely not, because that's just reflected sunlight, and sunlight is basically a continuum. However, the ions do produce emission lines. Indeed, a colleague of mine at Berkeley, Hiram Spinrad, he's an amazing guy. He studies the most distant galaxies and comets. So I remember as a postdoc under his tutelage, we'd go up to Lick Observatory and we'd take consecutive exposures, one of the most nearby objects in the universe versus one of the most distant. We take spectra. And those spectra show emission bands of cyanogen, CN, and various other molecules, okay? But they're mostly molecules, they might be ionized, it may be CN plus or something, but they produce these bands. And so you could enhance your contrast, but you'd need a very special filter, not your typical ring nebula filter, which transmits hydrogen alpha and doubly ionized oxygen. There's a pair of green lines. There's a few other lines. You know, the molecular bands are kind of at different locations, and moreover, they span more of the overall visible light spectrum. So you don't quite have as much to gain by using a nebular filter, in that you'd be allowing light from a broad range of wavelengths in, light from the tail and from the sky, and you'd be excluding a relatively small number of range of wavelengths, okay? So it wouldn't have as much of an advantage. But perhaps you could have a custom-made filter that's right at the peaks of these bands. I don't know of any such comet filters, though. But not your ring nebula filter, I'm sorry to say. Yes, way back there.
I kind of saw that the comet's revolving clockwise.
The comet's revolving clockwise. So in general, comets can come in from the Oort cloud, you know, in pretty much any direction.
Okay.
A periodic comet can be more or less 50-50 equal, though again, there I'm not so sure, because they're coming in, they might be coming in from, well, if they're coming in from the Kuiper belt and they get perturbed by one of the inner planets, then I would expect them all to, not all, but the majority to have the same sense of rotation as the solar system for those that are coming in from the scattered disk and from the Kuiper belt. The ones from the Oort cloud may well come in from pretty much random directions and be perturbed into a shorter period orbit, you know, essentially at random. This one is coming in, I don't know that I showed that. It's coming in from above the solar system, then dipping down for a very short time, then passing perihelion near the sun, and then coming back out. And that's where, if you plot it on the sky, in the right ascension declination plane, it heads off toward the North Star. But it's coming in at almost, but not quite, the plane of the solar system, yet it's not thought to be a scattered disk comet or a Kuiper belt comet. It's thought to be a comet coming in with zero energy. That means, you know, its orbit is such that it really looks like it's coming from the Oort cloud. It's coming in like this. And I don't think any of the planets are going to be sufficiently close to capture it into a shorter period orbit. I think, but I'm not sure, that Hale-Bopp was an Oort comet, an Oort cloud comet, but since then was perturbed into a 3,000 or 4,000 year period. I might be wrong on that. Don't believe everything you read on the internet. There are some sites, for example, that say that in the, you know, around December 7th or 10th, when the ISON is best, it'll be seen in both the morning and evening skies, and that's simply not true. It'll be too close to the sun above the eastern horizon, and yet there are some websites that will tell you these wrong things. So, I don't know, but I do know that some Oort cloud comets that were hanging around for billions of years out there took 10, roughly, million years to come to the sun. That's the calculation. If you do it, it's of order 10 million years. But then they were perturbed into several thousand-year orbits, and maybe Hale-Bopp is one of those. Again, does anyone know better than I do? It is one of those. Is it a 4,500 year period or something? Yeah. But was it already in that, or was its latest passage what put it in that 4,500 year period? Yeah, I don't know either, but it was an Oort cloud comet. Yes?
I think it started at 10,000 and went to the...
Beth says it started at 10,000. But it couldn't have started at 10,000 if it was an Oort cloud comet, because, you know, at 1 light year you do p squared equals r cubed, and you scale it to the Earth, and you come up with 10 million years, you know. So maybe it was a scattered disk one? That could come in from 10,000. So again, I'd want to see a refereed paper that says that it's 10,000. Maybe that's what you looked up anyway. Whatever, you know. So, okay, well, thank you very much. And enjoy.